Welcome to our deep dive, and today we're going to be exploring the mind-bending ideas of physicist Roger Penrose.
Oh, yeah. Penrose.
We've got excerpts from his work ready to go.
Excellent.
And I think this is going to be a really fascinating discussion.
Yeah.
I think one of the things that really struck me going through the material is just how many different areas his ideas touch upon.
He is wide-ranging, that's for sure.
Yeah, so just to give you the taste of what we're going to be talking about today, this massive objects act like clocks.
Oh, wow.
And the absence of mass, throws our ideas of time and space completely out the window.
Yeah, it's like it's the fundamental framework upon which we measure reality, right? And,
Yeah.
And if you pull that rug out from under us, then what do we have left?
Exactly. And then on top of that, we're going to get into his concept of a cyclic universe.
Yes.
Where there might be echoes of previous cycles of existence.
Yeah, I love that idea. It's so strange, and yet when you think about it, it has a certain elegance.
Yeah, and to top it off, we're going to be talking about his unique perspective on the Fermi paradox.
Oh, yes.
The puzzle of why we haven't encountered any extraterrestrial civilizations yet.
Yeah, maybe they figured out how to communicate across these vast cosmic epochs.
Right, like what if we're just not even listening on the right frequency or in the right way?
Exactly. We could be completely missing the signals.
I think the thing that's really exciting to me about diving into Penrose's work is that he weaves together physics, mathematics, and even touches upon the mysteries of consciousness.
It's heady stuff, but I think it's so important to grapple with these big questions.
Absolutely. So let's start with one of Penrose's most intriguing ideas, this concept that mass is actually connected to time.
Okay.
Now, we've all heard of Einstein's famous equation, EZC,
Right.
T Mott.
Yeah.
Right?
Of course, yeah.
But how does that actually lead to this idea that a particle with mass is kind of like a clock?
So it all starts with understanding what INSEAD is actually saying, that mass and energy are equivalent. They're two sides of the same coin. And then when we bring in Planck's equation, EHF, now this equation links energy and frequency, we start to see a really remarkable connection.
Yeah, Planck's equation basically says the higher the frequency, the higher the energy.
Right, exactly.
But I'm still not quite grasping how we get from there to mass having a frequency.
Well, it's a bit of a leap, but follow me here.
Okay.
If mass is the same as energy,
Okay.
and energy is inherently connected to frequency,
Okay.
then mass itself must have a frequency.
Oh, I see.
It's like every particle that has mass also has this internal rhythm, like a tiny little clock, and that ticking is determined by its mass.
That is so wild. Okay, so to make sure I'm following, does that mean a particle with more mass would have a higher frequency?
Yes, exactly, like a clock ticking faster.
Wow.
Now, this might seem really abstract, but it actually has real-world implications.
Oh, really?
Yeah, think about atomic clocks, for example.
Okay.
The most accurate timekeeping devices we have.
Right.
Well, they actually work by measuring the incredibly precise frequencies of atoms.
So you're saying the concept of mass as a cosmic clock, it's not just a theoretical idea, it's actually the foundation for some of our most important technologies.
Exactly. It highlights how these seemingly abstract ideas in physics can have these very real impacts on our lives.
That's pretty mind-blowing. Okay, so this leads me to a question that I'm really curious about. What happens when there's NO mass? Does time just disappear?
That's where things get really interesting because without mass, we lose our reference point for measuring time. Think about it. All our clocks rely on the oscillations of particles that have mass. If there's no mass, there's no clocks. And without clocks, how do you even comprehend time?
It's like trying to measure distance without a ruler.
Exactly. It just doesn't compute. So in a universe without mass, you could argue that both time and space would become meaningless. There's no scale, no framework for measurement.
So if we take that idea and apply it to the universe, does that mean the Big Bang, with all that unimaginable density, could actually be similar in a way to the very distant future of the universe when everything has expanded and cooled down and potentially become almost empty?
That's one of the implications, and it's a really challenging one because we tend to think of the Big Bang as this hot, dense beginning and the distant future as this cold, empty end. But in a universe without mass, those states might actually be fundamentally equivalent.
Okay, now this is where my brain starts to hurt a little bit. But before we go too far down that rabbit hole, I want to switch gears a little bit and talk about Penrose's idea of a cyclic universe.
All right, yeah.
Now, I know he's not the first one to suggest this idea, but what makes his version unique?
So a lot of cyclic models imagine the universe just kind of expanding and contracting like an accordion,
Yeah.
Repeating the same process over and over again. But Penrose goes a step further and suggests that each cycle might actually leave behind subtle traces.
Traces.
Yeah, echoes of the past that could potentially be detectable in our current universe.
Detectable echoes of a previous universe that sounds straight out of science fiction. But if that were possible, what form would those echoes even take?
Penrose thinks that these echoes might be imprinted in the fabric of space-time itself,
Okay.
in the form of gravitational waves from ancient black hole collisions.
Oh.
So imagine these ripples in space-time carrying information across cosmic epochs, giving us a glimpse into the universe that existed before our own Big Bang.
It's like a message from a universe long gone, a universe that existed before our concept of time even began.
Exactly. It's mind-blowing, isn't it?
It really is. Okay, I need a minute to process that. So we've covered a lot of ground already, from mass as a timekeeper to this mind-bending concept of a universe without scale. And now we're talking about echoes from past universes.
Yeah.
This is definitely deep dive territory.
It is, and we're just getting started.
All right, so stay with us, because next we'll explore how these mind-boggling concepts might connect to the Fermi paradox and the search for extraterrestrial civilizations.
Welcome back. We're diving back into the fascinating ideas of Roger Penrose.
And I'm really excited to talk about the Fermi paradox. Now, I've always been fascinated by this idea.
Oh, yeah.
The universe is so vast and it's been around for so long.
Right.
Yet we haven't found any concrete evidence of other civilizations.
It really does make you wonder, where is everyone?
It's like this giant cosmic ghost town.
Yeah, you'd think with all those stars and planets out there, there'd be at least a few other folks out there making some noise.
Exactly.
Yeah.
But Penrose offers a really interesting perspective on this that might give us some clues.
Oh, tell me more.
Well, he proposes that maybe, just maybe, advanced civilizations have figured out ways to communicate that are so beyond anything we can currently understand that we just haven't recognized them yet.
So instead of listening for radio signals or searching for spaceships,
Right.
we might need to completely rethink how we approach the whole search for intelligent life.
Yeah, exactly. What if we're just not looking in the right way or listening on the right... Well, frequency isn't even the right word anymore.
It might be something completely different. Think about it. If information can survive across cosmic epochs, even through the death and rebirth of universes,
Which is what Penrose suggests.
right, then wouldn't it be possible for a sufficiently advanced civilization to tap into that flow of information?
So you're saying instead of looking for signals traveling through space,
Yay.
we should be searching for whispers carried on the fabric of space-time itself.
It's a radical concept, I know, but it's one that Penrose takes seriously. He suggests that these civilizations might be communicating through something far more subtle than radio waves or lasers.
Like what?
Well, he speculates that it could be intricate patterns embedded within the cosmic microwave background radiation, or even subtle manipulations of gravitational waves.
Wow, that's incredible. It's like we're trying to listen to a symphony with earplugs in.
A perfect analogy. We might be completely missing the symphony of cosmic communication that's happening all around us.
This brings up another interesting question. If these advanced civilizations are out there, and they figured out how to communicate across such vast stretches of time and space, what would their motivation be for doing so?
Now that's the million-dollar question, isn't it?
It is.
Some people believe it might be a form of cosmic altruism, a desire to share their knowledge and wisdom with younger civilizations, kind of like a pay it forward on a cosmic scale.
That's a nice thought.
Others suggest it could be a way of preserving their own legacy, ensuring that some part of their civilization continues even after their physical forms are gone.
It's fascinating to try and imagine the motivations of beings who have transcended the limitations of time and space as we understand them.
It really stretches the imagination, doesn't it? And it forces us to confront the limitations of our own human-centered viewpoint. We tend to project our own values and motivations onto the universe, but the reality might be far stranger and more wondrous than we can even imagine.
Speaking of strange and wondrous, let's talk about another area where Penrose really challenges conventional thinking, his fascination with complex numbers and their role in understanding the universe.
Oh, yeah. The beauty of complex numbers.
I'll admit, math has never been my strong suit.
Oh, you're not alone there.
But I am curious to hear why he finds them so compelling.
Complex numbers often have this reputation for being difficult and abstract, but in reality, they actually simplify our understanding of a lot of physical phenomena.
Really?
It's like they're a secret code that unlocks hidden patterns in the universe.
Okay, I'm intrigued. Can you give me an example of how complex numbers are actually used in physics?
Absolutely. Let's go back to the idea of mass as a frequency we were discussing earlier.
Okay.
Remember we talked about particles having an internal rhythm like a tiny ticking clock?
Right.
Well, the math of complex numbers is essential for describing those oscillations in a precise and elegant way.
So these seemingly abstract mathematical concepts
Yeah.
are actually crucial for understanding something as fundamental as the behavior of matter.
Exactly. Complex numbers allow us to model the wave-like nature of particles, which is at the heart of quantum mechanics.
It's amazing how something that seems so theoretical can have such a profound impact on our understanding of the physical world.
It is a beautiful example of how math isn't just some dry set of rules. It's like this powerful language for describing the intricate workings of the universe.
That's a great way to put it.
Yeah.
I'm starting to see why Penrose finds beauty and elegance in mathematics. It's like he's using it to uncover the hidden poetry of the cosmos.
And that poetry extends far beyond physics. You know, Penrose also explores the potential connections between complex numbers, quantum mechanics, and even the nature of consciousness.
Wow, now that's what I call a deep dive. We're venturing into territory where physics, math, and philosophy all intersect.
It's enough to make your head spin, but in a good way.
Absolutely.
Yeah.
Welcome back. You know, it's really amazing to think about everything we've discussed so far with Roger Penrose.
I know, it's a lot to take in.
It is from the universe as this giant cosmic clock to the potential for civilizations communicating across vast cosmic epochs, and even the idea that information might be the fundamental essence of reality.
It's quite a journey, and I think one of the things that really stands out for me is how Penrose's work really challenges us to rethink our assumptions about the nature of the universe and our place in it.
It really does. And I think one of the most interesting threads that runs through all of his work is this idea that information might actually be a more fundamental aspect of reality than matter or energy.
That's a really key insight, and it has profound implications. You know, if you think about the laws of physics, the properties of particles, even the evolution of the universe itself, we can view all of those things as expressions of information.
Huh.
It's as if the universe operates on a cosmic code, a set of instructions that dictate how everything unfolds.
So if information is truly fundamental, does that suggest there might be this deeper level of reality?
Right.
Something beyond the physical world that we perceive with our senses?
That's a question that's puzzled philosophers and physicists for centuries.
Right.
And Penrose doesn't claim to have all the answers, but he definitely encourages us to consider the possibility.
Okay.
You know, he points to the mysterious nature of consciousness as a potential clue, suggesting that our subjective experiences might be a manifestation of this deeper level of information.
You know, earlier we were talking about how information might survive across cosmic cycles, but what does it even mean for information to be fundamental to the universe itself?
Okay, well, imagine a computer program.
Okay.
At its core, it's just a series of ones and zeros, pure information.
Right.
But from that simple code, you can have these complex virtual worlds emerge with their own laws, their own structures.
Yeah.
Penrose suggests that our universe might be something like that, a manifestation of a deeper informational reality.
So are you saying that our physical reality, everything we see and touch, might just be like a projection?
Yeah.
A holographic representation of this deeper informational structure?
It's a radical idea, I know, and one that's still being explored, but it's definitely a fascinating possibility. And it really highlights how Penrose's work pushes the boundaries of what we traditionally think of as science.
Right.
You know, he's asking us to consider a universe where information, not matter or energy, is the ultimate building block of reality.
So as we wrap up this deep dive into the mind of Roger Penrose,
Yeah.
if we were to step back and consider everything we've talked about today,
Okay.
what would you say is the biggest takeaway?
I think the most important lesson is that the universe is far stranger and more wondrous than we can often even comprehend. You know, Penrose's work invites us to embrace that strangeness, to question our assumptions, and to be open to the possibility that the answers to the biggest questions might be found in the most unexpected places.
It's a great reminder that the pursuit of knowledge is an ongoing journey. There's always more to discover, more to question, more to wonder about.
Exactly, and I think that's a beautiful and inspiring message.
It really is. So to our listeners, we leave you with this: keep exploring, keep questioning, and keep diving deep into the mysteries of the universe, because there's a whole world of wonder out there waiting to be discovered.